Hello, in this video I'm going to start looking at rectangular based collision systems, the kind of collision systems you would use on tile maps. And you may think, well, I've covered that sort of thing before, and you would be right to an extent. However, looking at the Discord users recently and just general the feedback I'm getting, a lot of you still seem to be having difficulty when it comes to tile-based collision systems. And I must admit that even I am fed up of coding the same thing over and over again whenever I'm implementing some 2D tile-based game. So this video is about creating a suite of utility functions which we can just reuse in the future for all of our rectangle collision-based needs. Now, there's something important to get out of the way at the start, and that is that yes, in this instance all of my rectangles are going to be axis aligned, and that means the rectangles won't rotate in any way. But that's okay, most 2D games don't require rectangle rotations. Now, there will be a little bit of mathematics in this video, but if you're not entirely comfortable with the maths, don't worry, we'll be looking at it in code too. And I know for many people, seeing it written out in code suddenly makes it understandable. Well, at least I'll try my best. And finally, for those following along with the progress of my lockdown goatee, it's doing very well, thank you. So let's get started. And I thought we'd start by going old school one lone coder just for a moment. This is a little project I'm working on in the background. The video isn't going to be generating this project, but it demonstrates nicely what it is we're trying to achieve. So here I have a big red rectangle in the screen, and you can see it's colliding with a tile map of smaller rectangles in the background. And I have a character with some very basic rudimentary physics, but the collisions are quite robust. Let's go down and find somewhere else to collide with. Here we go. I will be talking about this project at some point in the future. It's actually a little bit of groundwork for a future video I'm hoping to make about networking. But it also happens to describe collisions very nicely. So we can see the tiles in the background that are detected as being in collision with the red rectangle are highlighted yellow. It does also collide vertically, but because the frame rate's very quick and the collision is incredibly brief, you don't see it illuminate on the top axis of the rectangle. Many 2D games are structured this way, and it's a great way for beginners to get started with games programming, but coming up with a robust tile collision protocol isn't the most simple of programming tasks. So I hope that this video will sort of describe a nice suite of utility functions that we can come back to time and time again, so we don't have to keep recoding this stuff over and over. Since this is a video about all things rectangle collision, I thought we'd just get started straight away with some code and get the easy ones out of the way. As usual, I'm using a blank Pixel Game Engine project to start. You don't have to use the Pixel Game Engine to use any of these routines. And the algorithm should be quite transferable to whatever language you choose to use. We're going to be working with rectangles, so I'm going to create a simple rectangle struct to represent a rectangle, and bonus points for those that count how many times I say rectangle during this video. For my system, I'm going to describe a rectangle as being a point that defines the top left of the rectangle, and for that I'm going to be using the vector floating point 2D type, which is provided by the Pixel Game Engine, but that's just a pair of x and y variables. I'm going to call that pos. And the rectangle will be defined by a width and a height, its dimensions. I'm going to use another vf2d type for that, and call it size. The very first function I'm going to create is to check whether a point lies inside a rectangle. And yes, this is very basic stuff if you've seen it before. If the point lies in the rectangle, it's going to return a boolean. Point versus rect. And we'll pass in a point, and we'll also pass in a reference to the rect. To check if a point lies within a rectangle, we just need to make sure that the point lies within the four sides of the rectangle. So we take the point's x-coordinate. Is that greater or equal to the rect's position? And what we do for x, we'll always do for y. So that's checking that we're within the top left of the rectangle. We also need to make sure that we're within the bottom right of the rectangle, which is of course the rectangle's position plus its size. And that's that. Let's test it very quickly. I'm going to use the mouse coordinate to be my point. And in the Pixel Game Engine, we get the mouse coordinate by calling the getMouseX and getMouseY functions. However, these are going to be returned as integers, so I'm casting them to floats. We will need, of course, a rectangle to test this with. So I'm going to define a rectangle that begins with a position of 100 by 100 and has a size of, well, let's say 50 by 30. Now, if you're not familiar with this notation, I've used an initializer list structure to define my rectangle, because I've not defined any sort of constructor for my rectangle struct. So this is the position, and this is the size. I'm going to call the function we've just created, passing in the mouse coordinate and our rectangle, and if that's true, I'm going to draw the rectangle, taking its position, its size, and I'll specify the colour as being yellow, so we can see it. If I'm not in collision with the rectangle, I'm just going to draw it white. Because I'm changing what I'm drawing to the screen, each frame I want to make sure that I actually clear the screen. So I'm going to clear it to, let's say, dark blue. It's more interesting on the video than black. Right, let's take a look. So here we can see our rectangle being drawn on the screen, and when I put my mouse over it and anywhere within the rectangle, it turns to yellow. Next up, I'm going to create an equally simple function to detect if a rectangle overlaps another rectangle. I'm going to call this one rect versus rect and pass in two references to rects. This implementation is conceptually similar to the one we've just done, except now we're working with sides of the rectangles. I actually talked about this in a little bit more detail in my polygon collisions video earlier this year. I'll put a little link above. Fundamentally, we're now checking the sides of the rectangle. So considering the x-axis, let's test that the left-hand side of rectangle 1 is to the left of the right-hand side of rectangle 2. If that's not true, then rectangle 1 is entirely to the right of rectangle 2. There can't be a possibility of collision. If it's to the left, we need to make sure it's not too far to the left. And so the right-hand side of rectangle 1 must be on the right-hand side of the left-hand side of rectangle 2. This is going to be a fun video, this one, isn't it? I can already tell. And what we do for x, we also do for y. The principle is exactly the same, except left and right is replaced with top and bottom. And as before, we'll just do a very quick test to make sure this works. I'll keep the existing rectangle, but I'm going to need a new rectangle. I'll call that S, and its position is going to be vMouse. And we'll give it the size, very narrow, 10 wide by a tall 40 high. Instead of testing the point this time, I'm going to call our new function, rect versus rect, change the vMouse to an S, but we need to know where our mouse-related rectangle is, so I need to draw that rectangle too. And I'll draw that in green, why not? Let's take a look. So there's our green narrow rectangle, and if I overlap it, we see that the original rectangle turns yellow. And so there we have two very basic functions to detect if a point or a rectangle overlaps with another rectangle. We'll use these again later in the video, but some of you might be thinking, hang on Javid, you've already created a platform game before, you've made a video about it, and that had a tile-based collision system in it, and it didn't look anything like this. And you'd be right. But for those of you that haven't watched that video, let me just do a very brief recap on how that system worked. It did take advantage of a few tricks of the properties of binary numbers. In that demonstration, the world was broken down to a single two-dimensional array which began at 0, 0. And each element of the array represented whether a tile was solid or not. There was other information too to decide what the tile was drawn like, but principally we could determine if we should be able to pass through a tile or not. The principle was very simple. Here I've outlined 4 tiles as being solid, and my point within the world, let's say it exists here, has a floating point coordinate, which according to my crude drawing is about 2.6 in the x-axis and 1.4 in the y-axis. Assuming that all of our tiles take up 1 unit, and by 1 unit I mean that the dimensions across the tile are equal to 1, we can always determine which tile we are in within the array simply by truncating the coordinate. We can simply lose the information after the decimal point, and this will highlight which particular cell we need to interrogate in our array to see if it's solid or not. This is a technique I've used many times on this channel. Now let's assume I have a player character sprite, which is also 1 unit in size. I can check the 4 corners of the sprite to see if they land in a cell which is considered solid. Here we can see we're certainly in conflict with one of the solid cells, and so we need to position the sprite in such a way that it is out of conflict. And with this approach you always adopt a protocol. Firstly, we'll always resolve collisions in the x-axis, and then we will always resolve them in the y. And using these unit dimensions makes the resolution very simple. We know we are in conflict with this cell. We know where that cell lives within the world along our x-axis. We also know that the size of our sprite is equal to the size of a cell. Therefore, to resolve this conflict in the x-axis, our sprite must be positioned an entire cell to the left. So here is the sprite resolved in the x-axis. We can see it's no longer in conflict in the y-axis. There's nothing further to do. And calculating the position to place it was very simple. We can use truncation. The sprite was originally here, which is about 3.5. We can ditch the 0.5 because we know we're in conflict, and we're automatically aligned in the correct position along the x-axis. Here is a slightly more complicated collision. We've detected that the left-hand side of our unit sprite is in conflict with the tiles. Well, if it's the left-hand side, then we need to move it to the right. So we can take the position of our sprite and truncate it. That will move us to 4 in this instance. But we want to move to the right 1 whole cell, so we can add 1 to it to determine the correct location in the x-axis to be out of conflict. We can now do a very similar set of operations to resolve the conflict in the y-axis. This time we can see that our y-coordinate would be about 1.5. We truncate to tell us that it's just a 1, which magically resolves the sprite to the correct location. This approach is very simple and very effective, and the detailed implementation is provided in the Code It Yourself Simple Platformer game video. So why do we need anything more sophisticated at all? Well, there are scenarios where that approach has limitations. It required that the sprite we were using existed in unit space. It was 1 by 1 in relation to the tiles in the background. That can be quite a restrictive thing. What if you want a bigger sprite? The problem you have then is you are testing against tiles which are smaller and may have gaps, for example. Since we were only testing the corners, a tile that lies within the middle of the sprite rectangle simply isn't detected at all. We could resolve this by adding more test points to our sprite, but again it relies on these points all being a unit distance apart from each other. In short, it's not a very flexible way to do things. But that's okay, Jared, isn't it? You've shown us a way to detect if 2 rectangles are overlapping. Surely we can use that. Well, yes and no. Even that method has its limitations. Since we can now work with rectangles of any size, we don't necessarily have to have things aligned to tile boundaries. And in this instance, we can easily detect that the 2 rectangles are overlapping. And we could go one step further and actually resolve this collision. If we know that they're overlapping, we can sort of determine how they're overlapping and perform the necessary resolution to make sure that they are no longer overlapping. In this case, the green rectangle would move to the left by the amount it's overlapped. And that is a particular policy adopted by what is known as AABB collision detection routines, and it works just fine for most simple scenarios. Tricky scenarios, such as corner detections, again rely on a bit of a protocol. Which way should the tile be resolved in this instance in order to be out of collision? It's not that easy to tell. So one policy is that you measure the distance that it's overlapped in each axis. So here we've got it in our y and here we've got it in our x, and whichever is the smallest is the direction we resolve the collision in. And again, this works quite well and may be completely sufficient for your needs. But in, say, an action platformer style game, you may end up with some slightly unpredicted behaviour when you clip the corners of the rectangles. Let's say the character jumps onto a ledge but misses slightly. Well, have they missed or have they not missed? It's undetermined. The sprite could miss and fall down, or it could not miss and walk along the ledge. Displacing by this minimum overlap is a very useful strategy. But there's still a problem with it. And this becomes apparent when we start taking frames into account. We've got an object moving. Per frame, it's moving closer and closer to the rectangle. On this frame, it's in collision. And we can rightly assume we can resolve this collision by displacing the rectangle to the left. Good. Let's consider a different scenario. Our object is now moving much faster between frames. Following the rules we just established, now in order to resolve this collision, we would displace this rectangle to the right. It would no longer be in collision, which is good, that's what we wanted, but it's had to go through the original object. That's not good. And so fast-moving objects have the potential to penetrate through solid objects, which they shouldn't. And this problem isn't just restricted to fast-moving objects. What if the object we're potentially colliding with is very thin? The object could be moving slowly, but in proportion to the width of the object that we're colliding with, you still have the possibility of passing through it. So far I've presented a variety of ways to handle rectangle versus rectangle collisions and resolution, and it's up to you to choose which one is appropriate for you at the time. However, this video is about creating a one-size-fits-all solution, something I can just continuously reuse in future videos and future projects. And that's something we should strive to do as programmers. And the method I'm going to introduce next goes by several different names. Some know it as swept AABB, I know it as projected rectangle collision. And what we'll see is, yes, it's a little bit more involved, but it does cater for all solutions. So that's typically the trade-off we often pay when we look at abstraction. We're going to make it very simple for us to use in lots of projects, but it's going to be a little less performant. However, I think for almost all scenarios, this approach is probably the best approach to take. Before we can determine our general purpose collision detection and resolution routine, we're going to need to know if a ray intersects with a rectangle. Now, I did a video previously about the essential mathematics required for games development, at least what I think is required, and a great portion of that video was dealing with vectors. And we can define a ray as being a starting point and a direction vector. I'm going to call that starting point P, and our direction vector can be determined by some endpoint along that ray, let's call it Q, so our direction vector becomes D equals Q take P. It could very well be that D is some normalized unit vector, but in this case it isn't. I'm going to assume we can provide a start and an end point and use that to define our ray. This means we can define any point along this ray using parameter t. So if I take t equals our starting point plus our direction vector multiplied by t, then for different values of t I can get any point along this line. For example, if t equals 0, then I end up at just the starting point. If t equals 1, then I'm one whole direction vector added to my original point, which would give me the end. And therefore, if t is equal to 0.5, I get a point directly in the middle of my line. In fact, I can specify any value for t. I can specify negative values and go backwards. I can specify infinitely positive values and just keep going on forever and ever and ever. My rectangle is also defined with some vectors. So up here, I'm going to have rp for my rectangle's position. And as we did with the structure at the start of the program, I'm going to define the size of my rectangle as being rs. So this point is in fact rs plus rp. Now I want to do things a little bit backwards. I want to work out at what value t along my ray have I intersected with the rectangle. And as you can see, I can intersect with the rectangle in, well, two locations. And this is where we get to the rather odd notation of presuming that t is time, even though it's nothing to do with time at all. But from the ray's perspective, we encounter one point before we encounter the other. One is nearer to the origin of the ray and one is further away. Therefore, thinking of it in terms of time means we get to the first point before we get to the second point. So time is just a convenient form of language to describe this effect. And we can consider this point to be the time of our near collision relative to the origin of the ray, and this point to be far. One of our fundamental assumptions is that our rectangles are by definition axis aligned. They will never be rotated. Therefore, they will always have edges at 90 degrees to each other, parallel to the axes of our world. Therefore, I'm going to extend the edges of our rectangle infinitely long along its edges. And I want to determine what is the time to the near and far collisions in both axes. So now we can forget for a moment that it's actually a vector and deal with the components of the vector individually. So let's just take the x-axis as an example. Forgetting any y component of the ray, I know that my t along the x-axis here is equal to 0, and my t along the x-axis here is equal to 1. Therefore, this near point in time can be calculated in the following way. T along in our x-axis is equal to the rectangle's position dot x minus our point's position dot x, which gives us this length here, but we want that as a percentage of the whole length, and the whole length was our direction vector dot x. This gives us our near collision time. Our far collision time should be fairly obvious how to compute. It's this distance here. So our far, t at x, is equal to our rectangle's position dot x plus the rectangle's size now dot x minus our original points dot x, again divided by the whole length to give us that percentage. It's a percentage because it's between 0 and 1. So we can determine the t values for near and far along our x-axis. And what we do for x, we do for y. I'm not going to draw all those out, they're the same equations, but replace the x's with y's. Once we have established the near and far times for the intersections of the axes of the rectangle, we can sort them to see if the ray does indeed intersect with the rectangle. So let's start with a very basic example where we're going to go right through the diagonal of the rectangle, or square in this case. There's our ray, and we know that our near time in the x-axis will be here, and our far time in the x-axis will be here. They're also the same for the y-axis. So I'll put a little x and y next to those. I'm going to draw in another ray, parallel to the one that we had before. Now in this instance, our near time in the x-axis is here, and our far time in the x-axis is here. Near time in the y-axis, and far time in the y-axis. And I'll draw in a third ray, parallel but the other side this time. And we again can label our near time in the x-axis and far time in the x-axis, near time in the y-axis, and far time in the y-axis. And at this point we can observe something interesting. Our distance to the near time in the x-axis is always less than our far time in the y-axis. So here is the distance to the near time in the x-axis and our distance to the far time in the y-axis. This is even true for the ray in the middle. So let's start by assuming there is an intersection if our near time in the x-axis is less than the far time in the y-axis. We can also observe that our near time in the y-axis must be less than the far time in the x-axis. Let's draw in another ray and see if that adheres to these rules. To start it here, draw it along. It clearly doesn't intersect with the rectangle. Now the intersection point with the x-axis required the time to go backwards. That's quite strange, but it's legitimate. It's got to align with the left-hand side of our rectangle. So near x is up here, far x is here, near y is here, and far y is here. Is near x less than far y? Well, it is. Good. Is near y less than far x? No, it isn't. And that's because we've not had an intersection. So these look like some good rules to follow to see if the ray has intersected with the rectangle. But let's test it a bit further. This time let's have a ray going from down here and up. Here is our near time intersection with the x-axis and our far time intersection with the x-axis. And rather strangely, here is our near time intersection with the y-axis and our far time intersection with the y-axis. But this doesn't make any sense. From this origin's perspective, clearly the far and near times are the wrong way round. So we'll swap those and see if it obeys the rules. Well, nx will be less than fy, and ny is less than fx. There is an intersection. So it's important that we sort near and far in the respective axes to make sense before doing this check. Let's look at an oddball one. Here is the origin of my ray, and it's going perfectly horizontally through the rectangle. Here is our near time crossing in the x-axis and our far time crossing in the x-axis, but we don't get any crossings in the y-axis, and the maths will actually resolve to infinity. In this case, our near time crossing of the y-axis is minus infinity, because it's that way, and the far time crossing in the y-axis is plus infinity, i.e. it never happens. So do our rules still hold true? In this case, our near x is less than positive infinity, and our near y, which is negative infinity, is less than our far x. That holds true. Let's consider it from up here. Clearly it doesn't intersect with the rectangle anymore. Our near x and far x are the same as before, but our near y is now positive infinity, and in fact so is our far y. So is our near x less than positive infinity? Yes, it is. Good. But is our near y, which is positive infinity, less than our fx? No, it isn't. There is no intersection. And so it looks like sorting the values along the ray to be sensible, followed by this couple of checks, will give us an accurate assessment of whether the ray intersects the rectangle. Once we know a ray does intersect a rectangle, we can work out where. Here is our nx and our far x, and this is our ny and far y. In this instance, we can see that the intersection is occurring at nx, and nx is larger than ny. In this instance, let's put in our nx and our fx and our ny and our fy, which is down here somewhere if we carry on with that ray. We can see that the intersection occurs at ny, which is larger than nx. So I will make the assumption that the maximum of nx and ny is actually the distance along the ray to the first collision point. So t near is the maximum, nx and ny. Likewise, we can actually work out the far collision point, although it's less useful. Far collision point will be the minimum of fx and fy. We now have sufficient information to do a ray versus rectangle intersection test. So for now, I'll create a function which takes in a ray's origin point, the ray's direction vector, and a rectangle. Now, even though I'm using vector notation, in these next two lines I'm not actually calculating them as vectors. I'm using them as a convenience package to do the same calculations in both the x and y axes. So this division becomes an element-wise division. All of this is happening for the x component, and all of this is happening for the y component. And using the parametric line equations we talked about earlier, we can calculate our near and far points in time for both the x and y axes. If we end up in a situation where our far point is actually closer than our near point, then we want to swap things around. It doesn't make any sense to have something that is technically further away classified as being closer, so we'll sort them. And we know that we haven't got an intersection if the two conditions are not met. If we haven't rejected at this point, we can now calculate the actual times to the near and far collisions, using the maximum and minimum functions. For my implementation, I'm not interested in collisions that may take place entirely behind the ray direction, and so I'm also going to reject the collision if my furthest hit point is negative. That does imply that my closest hit point may also be negative. This is required because the maths works out. It says yes, there is a collision, but it's in the direction completely opposite to the ray direction specified. That might be useful for things, but not for this. Once I know the actual collision point in time along my ray, I can put that time back into my original ray equation to give me precisely this point. I can do one final line of filtering to give me just an extra piece of useful information. In this instance, I know that my direction vector was positive in both axes, and I can observe that if my near x time is greater than my near y time, and my direction vector's x component is positive, then the normal to the surface I'm colliding with must be in the negative x direction. I can construct a unit normal vector along the same lines, but the other way round. If my near y time is greater than my near x time, then I can assume my normal vector is in that direction. If my direction vector happened to be in the opposite directions, I can also calculate normals for the other two sides. Knowing the point of collision and the normal of the surface collided with is going to be necessary to resolve the collision. I want to pass these points back through the arguments, so I'll add some more arguments to my function. This is the contact point where the ray intersected with the rectangle, and this is the contact normal. I'm also going to pass out one additional piece of information, and that is the time to the point of contact. That's now coming in as an argument. I can calculate my collision point using the parametric line equation, and using a couple of nested if statements, I can construct the normal vector to the contact point. If I've gotten this far, I need to return true from my function. And so here in entirety we have the bare bones of a ray intersecting with a rectangle, and we're going to need that in order to handle rectangle versus rectangle collisions properly. We should test this to see if it works. I'm going to use my mouse cursor to define a ray from a fixed starting point, and I'll just choose that arbitrarily at something like 20, 20. My ray direction is going to be the mouse's current location minus the starting point. Now instead of drawing a rectangle, this time I'm going to draw a line from the ray's starting point, and I'll draw it to the mouse location, and we'll colour that green. The ray versus rect function we've just created passes back additional information through its arguments. We're going to get a contact point and a contact normal. We're also going to get a time to the point where there is a hit. So now I'll call the function we've just created, pass in the ray's origin, the ray's direction, the rectangle we're testing against, and then the contact point, the contact normal, and the time of the collision. This function returns true if the collision has occurred. Well, let's just test that to begin with and see what happens. So here we've got a ray and a rectangle, and as the ray intersects with the rectangle all across, we see it turns yellow. Oh, but it also turns yellow when we're not intersecting. That's interesting. But it does seem to only turn yellow when it's within the direction of the ray. The t that is returned will be 1 at the point of the mouse, and so we can ensure that t should be less than 1 for a collision. This time, no collision until the ray touches the rectangle. I'll now also draw in the collision point. I'll draw a small circle where the collision occurs. Specify a radius of 3 pixels, and we'll draw that in red. Let's take a look. Very nice. And I'll also visualize the normal. I know it exists at the collision point, and I will draw it to the collision point plus the collision normal. I'll pick a number times 10 just to scale that unit normal, and we'll draw that in yellow too. So no collision, and then we can see a quick little normal telling us which side of the rectangle we have collided with. So why have we gone to all of this trouble to determine if a ray intersects with a rectangle when we care about if rectangles intersect with rectangles? Well, recall before that there were problems if the rectangle is moving. It could penetrate the target rectangle in an appropriate way. I'll await the comments in YouTube below. But now, if we know the direction the source rectangle is moving in, and we know where it should be on the next frame, we can determine, well, hang on, during that movement there was a collision. This means we can no longer move through objects. We know a collision has occurred. Our t value is less than 1, and the function returned true. But if we simply displaced our rectangle to this collision point, we see actually we're still in collision. This is no good. We need to take into account the source rectangle's dimensions to resolve this collision properly. The simplest and easiest way to do this is to expand the target rectangle by half the dimensions of the source rectangle. Again, these are all tricks we can exploit because everything is axis aligned. So if I take the width of this rectangle and expand the target rectangle by width over 2 that way and width over 2 that way, and do the same for height, we generate a temporary artificial expanded rectangle around our original target rectangle. Now if we perform the collision check with the source rectangle and this expanded rectangle, the collision point occurs here, and when we resolve the collision, our original rectangle is directly aligned with the target rectangle. They are no longer overlapping at all. Now we've introduced rays with the rectangle. We've made an assumption that our rectangles have some sort of movement capability. Potentially they have a velocity, which changes their position. And so to our very basic rectangle structure, I'm going to add an additional vector, velocity. Now I'll add another function for checking a dynamic rectangle versus a rectangle. This implies that the rectangle is moving. And its arguments are quite similar to before. We take in the source rectangle, the target rectangle, and we'll get out of it a contact point, a contact normal, and the time of the collision. For the sake of this video, I'm going to assume that none of my rectangles start off in collision. Therefore, if it has a velocity of 0, the input rectangle can't be in a collision after calling this function. It's not moved. I need to expand the size of the target rectangle based on the dimensions of the input rectangle. And now I can call our ray versus rect function based on a point from the middle of our input rectangle. Our ray's origin is the center point of the input rectangle. The ray's direction is going to be the input rectangle's velocity. The target rectangle is our new expanded target, and our contact point and normal are the same as before. If the ray intersects and the length of the ray is less than 1, then I'll return true. Otherwise, I'll return false. A collision didn't occur. I'm going to modify the prototype of this function slightly. At the moment, we're passing in f_time, which is a return value of the contact time. I'm going to actually change that to contact time so it's clear, but I'm also going to pass in the elapsed time value of the simulation. And this is quite important. As we're doing things frame by frame, the velocity will be far larger than the actual displacement required for the rectangle. So I'm going to multiply that velocity by f elapsed time. We've seen this before in quite a few other videos where we update the position of an object by adding in velocity multiplied by f elapsed time. Because f elapsed time can be very small, the actual length of the ray that we want to test will also be quite small relative to the velocity associated with that rectangle. Now we need to add in some dynamics to the simulation. As this simulation develops, I'm going to need lots of rectangles. So I'm going to create a vector filled with our rectangle structures. And for this video, I'm going to assume that the 0th element of this vector is the one that's under control from the user. So we need to establish a few rectangles here first. The player rectangle, I'm going to start out at 10, 10, and give it a size of 30 by 20. The velocity will be defaulted to 0. I then need to add another rectangle to the scene. I'll position that at 100 by 100 and set it to 80 by 50. I'm going to make it so that whenever the user holds down the mouse button, that the rectangle's velocity vector is set towards the mouse. So I'll take the ray direction we calculated earlier, I'll normalize it for now, just so it's a sensible value we can play with, scale it so it's not very slow, then also modulate it with f elapsed time. And I'll use a little auto for loop to draw all of the rectangles in the vector. I want to perform a collision test between the 0th element, which is the player rectangle, and the other rectangles in the vector. So I'll just iterate through those manually, not including the 0th, because I don't want to test that against itself. And I'll test against all of the rectangles. vrect0 is the player, vrect_i at this iteration of the loop is the target that we're testing against, and I'm going to be getting a contact point, a contact normal, and a contact time, but I also want to pass in the elapsed time for this frame. If that returns true, for now all I'm going to do is simply set the player rectangle's velocity to 0. We can get rid of all of this. Finally, I actually need to update the position of the player rectangle. So let's take a look. So here we've got the two rectangles, and as I hold down the mouse button, I can change the velocity of this player rectangle. So let's see if it crashes into the rectangle. It didn't. Good. And I can move it back off. Let's try that again. That seems quite nice. Let's try it from this side. Yep, didn't seem to do it. Good. Collision is working nicely. Just clipped it and we can come back off. I'm going to try really fast velocity into the rectangle this time. We really smashed it in. And now I can't click it off. That's because, yes, we've detected the collision, but all we've done is stop the velocity of the object. We didn't resolve any collision here, and consequently the two rectangles are still overlapping. And if they're overlapping, then the velocity just gets set to 0. So these are permanently stuck together now. What we need to implement is proper resolution of this collision. To resolve the collision properly, instead of just stopping at 0, I want to cancel out the velocity in the direction of the contact normal. Consider this source rectangle coming into contact with this target rectangle. It's overlapped slightly. We know that this displacement is equal to the length of our ray. Therefore, the time of the full displacement is 1. And because we're dealing with axis-aligned rectangles, we can take any point on the rectangle's perimeter, look at the corresponding point on the next frame, and the distance will be the same. So we know that this whole travel here is equal to 1. When we called the ray versus rect function, we were able to return the actual time of the collision, which has to be less than 1. So we know that this duration here is t, therefore this little duration here must be 1 minus t. Whatever velocity was specified on the rectangle to put it into collision, I want to work out a little bit of reverse direction velocity to move it back out of collision. Well, at least to stop the rectangle from colliding in the first place. Well, this little portion of velocity can easily be calculated as velocity scaled by 1 take t. But I only want that to apply in the direction of the contact normal. So I can element-wise multiply that by the contact normal, Cn. I'll change this dead stop to be a modification of the velocity. I'll take the contact normal, element-wise multiplied by the velocity. Now I'm going to do something a bit strange here. I'm going to take the absolute values of the original velocity, because I only want to take the polarity of the contact normal into account. If you want a more mathematically pure way to do this, you can do it with the dot product. But this is a nice little hack. And finally, I'll multiply that by 1 minus our contact time. This gives us the situation that if the dynamic rectangle intersects with the static rectangle, its velocity is altered as such that it can't penetrate the static rectangle at all. The nice bonus side effect to this is we don't alter the velocity in the opposing axis to the one that we've come into collision with, which gives us the ability to slide along the edge of the static rectangle. So let's take a look. So I'll give my source rectangle some velocity, and we see when it came into collision, it now starts to slide nicely along the surface. Let's try it along this edge too. We're no longer in a situation where the rectangle is getting stuck in the static rectangle. I can come back off it. Nor do I lose velocity in the axis I'm not in collision with, which means I can have a character or an object run across the top of the rectangle, for example. Very nice. I've gone ahead and added a bunch of rectangles to our playground. Let's take a look. So here I've got the player rectangle in the top corner, and we'll try it in different configurations. I've got two large overlapping rectangles forming this plus shape, and it seems good against the inner corners. Here I've got a little spurious rectangle sticking out, and we can quite happily see that the player rectangle collides against both and doesn't allow any further movement. This is what we would expect. At the bottom, I've got a scenario where I might have something like a character running across a set of tile objects. So I'll pull the object over here. It's good, gets very fast, very nice. Let's go back, try again. And you'd be fooled into thinking that, well, we've done it, this is easy enough. The problem we've got is when I attempt to slide in the opposite direction. It just doesn't like it. What's going on here? It's as if the player object is getting snagged on the corners of these tiles.
And this is quite an interesting bug, but it's one that's vital that we squash, because we can't just have games with our characters always running in the same direction. It is also quite a complicated bug to work out.
And it's bugs like this that give collision detection a reputation for being hard. You think we're done with the complicated maths and physics, and then all of a sudden you get a nasty bug like this. The problem is the order of testing is insufficient. When I've constructed the rectangles for that platform at the bottom, I've constructed them in this order in our vector. As the player object is moving along the surface, it's being affected by velocity in two directions. It's being moved along, but there's also gravity pulling it down. This means as each frame is progressing, we're actually checking for a collision of the player object in a location like this, and we can see it collides with the tile that it is sat upon, and it gets resolved appropriately. It gets nudged back up, and it's moved along. It's exactly what we want. Then we hit this situation, at an edge between the two tiles. The player object is tested against the tiles in the order that they were put into the vector. So it's tested against number 1, there's no collision, nothing to worry about. Tested against number 2, it gets resolved appropriately, its velocity is changed, so that's put it in the right location. Then it gets tested against number 3, there's no collision anymore, the velocity was resolved with square number 2. And so moving in this direction, things work as intended. When we're moving in the opposite direction, the same applies. Gravity is pulling it down, and the character has a leftward facing velocity. But we check against the order the tiles are stored in the vector. So the first thing we'll do is check collision against this tile. Well, in this instance, the collision has resolved to push the tile this way. That's okay, I suppose, but it means we've not travelled as far left as we should have done. Then when we check against tile number 2, we correct vertically. At high frame rates, this gives us the impression of just simply sticking at the corners of tiles. At low frame rates, what you may see is we move across the tile at the expected velocity, and then we take a sudden slowdown as we go over that transition. It doesn't move smoothly. To compensate for this, we need to check collisions in order of their proximity from the source rectangle. And to determine the proximity, we need to have calculated the collision. There's a bit of a chicken and egg thing going on here. So clearly the first thing we should be checking against in this instance is tile 2. And then potentially tile 1, and then tile 3. Since our ray intersect function returns a collision time, we can assess the collision times for all of the rectangles that we're testing at one instance, sort them, and then perform the collision resolutions in the sorted order. And as soon as you mention sort, people start to groan because you think, well, hang on, that's going to be really computationally intensive. And to be fair, those people would be correct. However, we can do a broad phase pass first to determine which tiles we're likely to be in collision with. In my little example here, I'm testing the player rectangle against every other rectangle in the scene, and it's happening quite fast and we don't notice any difference. But if you're showing potentially 1,000 tiles on the screen, and you're checking against all of them, there's literally no point. Your frame rate will drop to nothing. So we need a way to quickly discount tiles that we know we're not going to be in collision with. But first, let's deal with our sorting problem. And I'm simply going to brute force this. Typically, this is something you would hide away in yet another layer of abstraction, but I'm going to keep it open here so we can understand the algorithm. The first thing I'll create is a vector of pairs. Now, a pair is just a very quick and convenient data structure to hold 2 items of data. In this case, it's going to hold an int and a float. And when I detect a collision, instead of resolving it, I'm going to store into my vector the index of the rectangle I collided with and the contact time. I'm then going to use the standard sort function from the standard library, which has a quick little lambda function in it to sort my vector of pairs based on the contact time. So the lowest contact time will be resolved first. Now I'm going to iterate through the sorted vector of pairs, this time calling again my dynamic rect versus rect function, but passing in the index associated with the pair I'm currently processing. This is clearly redundant, and I'm hoping you can see there are ways to tidy this up when you're dealing with a selection of rectangles being tested for collision at a time. Now I know that I'm colliding with the rectangles in distance away from the player rectangle, I can resolve them appropriately. So a quick recap, we do a first pass of the collisions to work out what is the appropriate order the collisions need to be performed in. We sort the results to make sure that we're dealing with the closest collisions first, and then we actually perform the collision resolution by adjusting the player object velocity. So let's take a look. So as before, it doesn't affect our normal way of performing collisions. That seems okay. And I can move the player to the left, and I can move the player to the right. Left and right. And we see we don't now stop at the corners of the tiles. Gravity is inferred because I'm holding the mouse button below the row of tiles. But there is one final little problem. This looks all well and good, but when I release the mouse button, it stops on the next corner. What's going on for that frame? The velocity in that direction is being instantaneously set to 0. We don't notice it when I hold down the mouse button because each frame we reset the velocity based on the mouse's location. This took quite a bit of debugging to figure out. But the answer lies here, and you should always be aware when you're dividing numbers. There's a potential here for divide by 0. Now I'm quite sure there are super elegant ways to deal with that situation, but I'm just going to simply check that if a divide by 0 has occurred, therefore resulting in an invalid number, to simply say no collision has occurred at all. Our algorithm actually relies on divide by 0 to give us the plus or minus infinities that we required during the raycasting operation. However, in the event of the velocity being 0 and we divide that by 0, then the floating point standard dictates that the result is not a number. It feels a bit hacky, and that's probably because it is. But it works very nicely now. We can see the character, with me not holding down the mouse button, is no longer prompted to stop when it hits the corners of the tiles. I just wanted to try this one out just to make sure. Yes, there we go. Very nice. Now, as usual, I always provide the source code for every video that I make, and in this instance, the source code is a little bit different to the video code in that I've wrapped up these functions in a convenient to use way. And there are a lot more comments too, so if you've not fully understood this video, do have a look through the source code. And you'll see that I've also included a way to know which rectangles you have collided with. This could be very useful, for example, if you wanted the behavior to change depending on what you have become in collision with. But it's also useful to know in case you want to handle the collision response differently depending on the side of the rectangle you've touched. I've got two little notes I just want to finish the video off with. If you've still constructed your world using tiles, then it makes sense to extract each solid tile as a rectangle and use it in the algorithm. And I briefly mentioned that it would be inappropriate to test your moving rectangle against every possible tile. However, we can exploit some of the properties of tile grids that I showed at the start of this video to determine an appropriate region of tiles to select in order to generate rectangles from. Here in green, I have my source sprite on one frame, and because I know the velocity of that rectangle, I can determine where it's going to be in the next frame. Because I know the position of the rectangle before and after the movement, I can surround this with one large rectangle. And I can use the truncation properties that we discussed earlier in the video to determine a far smaller subset of tiles which are the only possible candidates for this collision. In practice, this subset will be much smaller than your overall tile map. And this is a great optimization you must perform. If, however, your level is constructed out of arbitrary rectangles, then you will need a different spatial separation structure in order to optimally cull the rectangles you needn't bother checking, and I think this will be the topic of a future video.
And so there you have it. Quite a tangled video this one, but nonetheless I feel quite important. We've handled pretty much every possible type of rectangle collision that there is. It's important to remember to choose the most appropriate form of collision detection for your application. Now, this may be the first of a couple of videos regarding rectangle collisions, because it might be interesting to look at now dynamic rectangles versus dynamic rectangles and how we can shift mass about, like we did with the programming balls videos. Regardless, the source code is available on the GitHub. If you've enjoyed this video, give me a big thumbs up please, have a think about subscribing, and I'll see you next time. Take care.